Hello, my name is Jessica, if you don't already know. I'll be presenting a paper on verification.
So, by the way, on Zoom, the audio is very low. So, um,
Oh, you can't hear. Uh,
yeah, it's very hard to hear. The
okay, can you
audio
hear now?
volume, yeah, it's just better.
Okay. Okay, so in this paper, this is how it's gonna go. There's a lot of info. And so this is all what I'll cover.
Is it better now?
Yes, yes, yes. It's okay now. Yeah.
Okay.
Okay, first I will introduce you, give you a small introduction to CNN, work with it. I will describe what image stars are and how we are going to use it in this verification method, give its reachability for different kinds of methods, then compare it with other verification models like polytope and poly. Okay, just before I start, if I miss anything, kindly ask questions. Okay, so convolution neural network is a special type of DNN. So, and it's specifically made for images. So when you see an image, what do you see? A few lines. Like you see, if you're checking for a human's face, you'll check nose, eyes, hair, ears. But if you pass an image through a DNN, all the pixels are independent of their position. Like it doesn't really matter where the ear is, how close the ear is to your eye or whatever. So what convolution network does is that, for example, you're checking if that image has a nose in it. Okay? What do? Just like you put like a small area around your face. You just need to check the area where your nose is. You don't need to check your entire image. So what in convolution network we do is we sort of have a small filter, which is usually like a 3x3 or a 5x5 kernel matrix, and we pass it through the images in somewhat like this. Uh, so, so what this does, it brings out the features in the image. For example, if you're seeing this deer, now the background of the deer doesn't really matter to us. The features of the deer, that's the ears, shape, and etc., what we care about, which we can bring out using this filter. So, yeah, just like I said, you have a small filter, you pass it through your every small local region, which is this in your matrix, and you get a special value. So there are different types of layers CNN adds to a generic DNN. So the first type is a convolution layer, which the filter is basically a 3x3 matrix with these values. And you just do like a dot product with every region, and then sum the values and get this. So you do that for every possible region, and you finally get a convoluted feature. So this is, and this feature would, so depending on how your filter is, the feature it extracts would be different. So which feature is extracted is something that the CNN will decide on its own. Okay.
Go back. I mean, so the window is actually moved one at a time, right? Because there are three things there because the window is moved.
Moving. Yes, we are checking every single 9x9 region you can get in the matrix. Yes, and okay. So there are two more additional layers that CNN adds, which is an average pooling layer and a max pooling layer. So what it does is, in this region, we dot producted the values, right? But instead of dot producting, you see the yellow box, you find the average of all the values in the yellow box, which is average pooling. And in max pooling, you find the maximum value, which in this case will be 1 in the yellow box. Yeah. And since, like I said, CNN is a special type of DNN, it still has the layers we use in DNN. It's like fully connected layers, ReLU, patch normalization, which is exactly how it works in a DNN. Okay. So you know the classification part, which looks exactly like we do it in DNN. So what we do is we pass it through several convolution layers, average pooling, ReLU, and then finally you will get like a 3-dimensional structure or several dimensional matrix of sorts. And then you flatten it and then just do a basic DNN. So this is just an introduction to CNN. We'll get into it deeper later. So I'll explain the abstract of this paper. So CNNs are redefined state of art in many real-world applications such as facial recognition, image classification, etc.
There, just one simple, questions. Since I'm not designed or trained a CNN. So one question is, how do you decide when you use ReLU pooling?
I mean,
I know that it's not as relevant for your verification method, but this is just a general
when
question.
to use convolution.
Yeah, I mean, how do you, you've shown, is this the order in which it is done, or it is intermingled, that hidden layers before the fully connected layer?
Like what we...
So the ReLU and the pooling, max pooling, etc. How were they decided?
So, I mean, just like any DNN, we'll have to have an architecture. So in the architecture, we will not specify which kernel you give, as in which filter you give. We just specify the size of the filter and then let the CNN learn what the values are. And for max pooling, you have to specify it's a max pooling. But usually you use it when you have a big image and you just want to keep making it smaller and smaller enough to get the right size.
So the other part of the question, general question, is because the kernel itself has weights.
Yes.
Okay? Those are the only hyperparameters. So of the
convolution. Yes.
Yeah, the convolution layers.
Yes.
So during the training process, the entire thing is trained together, I presume. No?
Yes. Yeah.
Okay.
So, like I said, CNNs are like state-of-the-art real-world applications such as facial recognition. But like any others, a neural network, it can have adversarial attacks. And this is a type of verification that makes sure if it can survive an attack or not. So in this paper, we come up with a new set of, okay.
Yeah, so you used like a DNN at the end, right? Classification.
Yeah, sorry, yeah.
So my question, I was just curious whether you can use convolution all throughout and just get a one single element. Like,
I mean, after some point, this box will be small enough for you to have, like DNN it's a type of convolution, right? Like in convolution, you just have small number of weights which are uniform. But neural network, you have more weights and the whole image is considered. So like it's more complex, but it's kind of better, right? Because you are kind of making use of all the weights. So the end, if you have only a few features and it's not complex enough, it's better to just use a DNN at the end. But you can not use it.
So in a way, you're saying like CNN is more like a subset of DNN in terms of expressivity.
Yes, but there's also like you have to use a few convolutions. Like I said before, DNN does not actually like it's just like a DNN. You use an array, right? So you don't really check if the two arrays are close enough. You don't like none of that is actually known by the neural network. For example, in an image, you have these 2 points which are close together, which is really important for classifying it. The DNN might not be able to get to know that, because it might move around. Like it's an image, you move around, like the face moves around in the image. Then the CNN will get to know because we're getting out the features. But the DNN would not, because they don't.
You can always.
Yes, but it's more complex, like I said. Yeah.
Just on this point,
Yeah.
like the question
Just
is.
a minute, show your hand.
Oh, yeah, sure.
Yes, question was, one is why you need CNN. That, at least to me, is clear. It gives certain correlation, like that, the positions and the correlation between these cells that are grouped together as how it varies. Window is and also it gives some compression, okay, out certain things. So the other part of the question, why have just that answers why you need. Thought your question was, oh, I have all of them as CNN, but then CNN's learning part is not just gradient descent is used.
Because the CNN gives you the features, but they don't know which feature is for which, like which feature helps which, just learned by the DNN.
I mean, at some point at the end, you have to have a selection.
Classification, etc. There. So, Diganta, you had some comment?
Oh, no. I was just asking this question only that it is true that CNNs are strictly speaking like DNNs are, the explicit power of CNNs is no more than that of a DNN. But the idea is that it's more parameter efficient, right? So is that a good way of looking at it?
There is more parameterization
in DNN. So CNN,
DNN.
Yeah. So CNN is more efficient that way.
Yeah. They're pure parameters.
Yeah. So if you have
any other questions, general questions on CNN?
Okay. So in this paper, we introduce a new type of abstract domain called image star, which we have found out to be more faster and less conservative than the zonotype and polytype methods like deep poly and deep set, which I have earlier discussed. Yeah. So let me first explain what an image star is. So image star is a type of abstract domain. It's represented in the form of C, V, and T, where C is the anchor image, which is the image you're giving, which you want to basically give the adversarial attack to. And B is a set of generator images, which represent the adversarial attack, which pixels you will aim at, which attack. Yes. And P is the predicate we use to bound the alphas. So an image star is represented as any image of the form C plus sigma lambda I vi, where vi is the generator images. And the predicate is so that we can bound these lambda i's. So we can't have just unbounded lambda i's given. The predicate will bound the lambda i's, basically. Sorry, alpha. Alpha, yes, sorry. Yes, and so this predicate can be written in the form of C alpha less than or equal to D, because it's basically of many linear inequalities, we can just be written in the form of matrix. Yes.
Wait a minute. So go ahead. Somewhere you snuck in the word attack, attacking images. No, that kind of threw me off. Can you?
Okay.
So far, you're not talking that. Also,
okay.
You should explain.
Okay. So
that.
for now, if you're not adding the adversarial attack, just consider V as just generator images, just another image which you can add to your anchor image. I'll explain later why it has to do with attacks. Just to
okay, so you get the example. That's okay.
So just to visualize, C is your image and V is your generator image. So you give a bound on alpha between 2 and -2, which is what the predicate does. And then, so it's basically like darkening this particular pixel or darkening or lightening that pixel, which is, kind of like an adversarial attack where you brighten a pixel or darken it. So I'm assuming image star is clear? Or
so I guess V specifies
how
in
the
the
attack.
pixels, how they are changed. Okay,
Yeah.
right?
Yeah.
And
how much is
decided by P?
Alpha.
P.
Yeah. P is just bounding the alpha.
So, but there is this alpha,
yeah,
which is the, I mean, that's also, how is that determined?
So this alpha.
Here it is 1 minus 1. Why would you want to vary alpha? I mean, that's a scaling factor.
Yeah, that's how far you can. Yeah, like an interval, you have everything between two numbers. So just like that, you have everything.
So in this case, it's only there is 1 and all the others are 0 in the V vector.
Yeah.
So only pixel in that position
only
is
pixel
disturbed.
In this will be affected.
That is changed within 2 and 2. So as a linear combination of.
So only thing the predicate must make sure is that the alpha is called the predicate variables. So you can just write this as alpha minus alpha less than 2.
I just asked why is between -2 and 2.
So this is just an example. I guess. Yeah, we can choose it to be whatever you want. So only thing you need to make sure the predicate does is bound all your predicate variables, because you don't want to have a very huge image star.
Are you saying that because of the way that P is defined, it bounds alpha by -2, or this is separate from that P?
No. I'm just saying this represents that.
Okay, so how does that?
It's alpha.
That's a vector or a range?
So it's C alpha less than equal to D, right? C here is 1 minus 1. D here is 2, 2. Alpha is? Yeah, alpha is a scalar. Wait, sorry, I had to mention that earlier.
I mean,
alpha
in the paper, he does mention alpha can also be alpha is not just a scalar, actually it's a vector.
Alpha is a vector in the dimensions of the, in the, what do you call it?
So just to understand the notation, alpha I is a scalar, but if you consider all the alphas together, they form a vector. Is that correct?
Correct.
Yes, right. So here, in this example, you have exactly one alpha, but like I stated, alpha can have several alphas.
So in that example, because there was only one position in which you think, so alpha was just a vector of length 1.
Okay, yeah, sorry, alpha is the scalar. Here, in this example, it's a scalar, all alpha is a scalar.
Yeah.
Okay, so this whole paper roams around the idea of a
I don't know,
reachability.
I have a question. You know, you did mention whether it is you want to take this question at this time or later on. So I'll ask it anyway. Suppose you did not have image star, and you said you could have used some other domain, you know, like, of course, D poly uses interval domain, just the bounds on your inputs. Or you can have more powerful domain. You did mention zonotope or polytope, although you may have to describe what that, I mean, if suppose you did not have image star, and suppose you wanted to express it in simpler domain, what does this give you? More expressiveness? I know it is structured. Your set of images is somehow structured in the way that you perturb them. Okay, that is captured explicitly by another term. But if you were to be, you know, if you were representing using interval domain, then the only thing you could have said is these individual values can be perturbed between delta, you know, some delta and some other delta, right? So what is this giving you in terms of that a simpler domain like interval or zonotope or, you know, polytope is not giving you?
So the main contribution of this paper is how reachability is done. Like after you pass an image star through a layer of a CNN layer, what is the next image star you get? How tight is that? How over approximate that is? In this paper, we'll see that image star almost gives an exact analysis at times, which is not possible in polytope and zonotope. Like it's possible in best case scenarios, but it's not as often. We will see the comparisons later, and it would be visible. Like like as an abstract domain, they kind of look similar, but the reachability methods used later is possible only for image star and not in case of an interval.
Well, then I'm not sure. I mean, I know reachability on image star they have done in the paper, but if you're representing your region of your set of images, could be represented as polytope or a zonotope.
Yeah, but
so there are methods to compute reachability over those shaped regions as well,
which is not as easy as you can do with an image star.
Okay, so you can do that.
Complex.
Yeah, but this is much easier is what they claim.
Yeah, so I think that this discussion, I think it might be good to revisit this when we talk about the experiments, because the experiments actually explicitly try to demonstrate this, that the expressive, or at least the over approximation quality of.
So that's why I said that maybe it's better to defer.
Yeah.
But one thing is not clear to me, and we can probably revisit when we're discussing the comparison experiment section, is why this way of representing image star, if it gives you any more accurate way of representing sets of images over if you were using zonotopes or polytopes. Of course, polytopes, specifically polytopes. I mean, interval domain, I can understand. This is more powerful than interval domain because it's considering anyway, let's defer that. Okay, that is some question that I did not have an insight into when I read the paper. So
in the experiments, they make it like we can see a very drastic difference between the two, which we will show when we do the experiment.
Yeah, okay.
Yeah, and as to why that happens, I think that's a very interesting question, which let's discuss that during the experiments.
Fine, I'll wait.
Yeah, I think it's yeah, sure.
Okay, so here, the reachability set, the image star is basically a type of abstract domain. So what we do is we pass what we need to find. If you pass an image star through a layer, what's the next image star you can get, which is the best over approximation of gotten, right? So this is how reachability set of a CNN is defined. Let I be your input image
So
star.
wait a minute, just to correct you. I heard you say image star is just a over approximation or something.
Like if you pass all the
If you
images,
pass, you may or you may not use over. Image star is basically a representation, a special kind of representation for a set of representing a set of images. Correct? It's only when you pass your through
the layer,
layers,
you get
you may do it precisely or you may not
get
get
an
over approximation. Okay? And that's what you're
Yeah.
trying to describe here.
Right. So if I use the input set, which is an input image star, and you pass it through the, like LIs are all the different layers in your CNN. Let L1 be the first layer. You pass all your input images through the first layer, and you make a set of all these possibilities. Then the abstract, the abstraction of this set in image star will be RL1, which may be an over approximation or might be precise. So we do this sequentially till you get the final, which would be another image star of Rn. Here, the abstract domain is not exactly image star, it's a finite union of image stars. You can have several image stars. Okay.
Go back. Any questions about the general reachability definition? Anybody? Okay.
So this is how you check robustness check in this. If you have understood reachability, after you pass an input image star through our reachability procedure or algorithm, you will finally get an Rn, which is an abstract interpretation of all the possible outputs you could have obtained by passing the input set through the CNN. It could be over approximate or precise, like I've said earlier. So we say an image CI is robust if every image in Rn, which is final output image star, gives the same result as your anchor image, which is CI. So no matter how many lambda VIs we add to the image, it should give the same classification or the same result, which is what we need to check since, right? So if we find out that Rn gives the same result for every value in it, then we say that the image is robust. It can survive whichever attack that is supposed to be in here. But since Rn can be an over approximation, even if we find out there's a value in this Rn which does not classify the same, it doesn't exactly mean that the input set is not robust. It's an over approximation. There could be some value that the CNN could not have reached, but is classified wrong. Okay, so the main part of the paper is how this reachability is calculated. So in CNN, like I said, there are 6 types of layers. And I will individually tell you how reachability is calculated for each one of them. First, I will tell you what an affine mapping is. And
how is the final check done?
So in I
know that the rest of your talk will describe how you compute, how you propagate this set to each of those layers. But my question is, at the end, when you get an image star representation of Rn,
yes,
whether that thing, every image in that set,
because it's in the form of an image star, we have a method to, like, since we know
that's a simple
lambdas,
check, isn't it? So
yeah,
you just
it's a
have
very
to get
simple
the
check.
output of
Yeah,
the
we
thing.
just need to check like the argmax, which is a simple. I will explain all that later. So for now, what's an affine mapping? So any linear operation, okay, wait, an affine mapping, a mapping L, if you say that it has a scalar factor gamma and an offset image beta, it can be written in that form. the function. So an affine mapping is if you have an image star lambda and you have a scalar factor gamma and offset image beta, then after you pass it through L, you'll get lambda dash, sorry, beta dash image star, which can be you can just change the anchor image, which is C dash is equal to gamma into C plus beta, B dash into gamma into B for generators, and keep the predicate same, as in you don't have to calculate for the entire image. So like I've shown here, if any element of image star is of this form and you pass it through the mapping L, you can just move them around and get it in the form of C dash plus lambda V dash, like in this form of the image star theta dash. This is a property of the image star which we use. So I hope this is clear.
Why is P prime is said to be the same as P?
So because here when you, like the lambda is fixed, at the end the lambda is, sorry, alpha I, alpha I remains the same here. So changing the predicate does not change, like when you do a linear operation as such.
So you're keeping the alpha the same.
Yeah. So any linear operation can be written like like an affine mapping. Any linear operation can be written in the form of some L, and you can do the same mapping. You can just change your anchor image, your generator image, and get the next image star as such.
Yeah, so here, go back to the thing. I think I'm going back to Shubman's comment. Okay, so you did say that I know alpha and that del constant less than or equal to, that you could have anything you want, but here you're keeping it for all the layers the same.
D is fixed, like.
Yeah, D is fixed.
Yeah.
The alpha
changes according to the bound you have given here. Like
but they don't change for every layer, does it?
Which we will, like for the linear ones, like in this case, the convolution is a linear operation. You're basically just multiplying element wise, which is basically a linear operation. You can just do the same, which is
just a second. Just to understand the question. So the previous question, I think, sir, you were asking whether this alpha is they change or not when we go from layer to layer.
Yeah, I think I was motivated by the fact that I'm trying to understand why P should remain the same. Jessica said, or at least the way I heard it, that alphas are the same and therefore P can be the same. It's something what you said. Okay, that kind of confused me. So does that mean that alpha it remains the same when you do this across the layer?
So what we're trying to show is if you pass the entire image star through L, you'll get this image star. So we need theta dash to represent all possible outputs, right? So from here, you know, everything can be written in this form. Any output can be written in this form. And here, the bound for the alpha is the same as the bound earlier, and we see no necessity to change it.
Yes, I can see this in for the affine transformation. Whether this will apply for others, I don't know, but let's see here.
No, it doesn't apply for others.
It does not apply for others.
Affine transformation.
It's only for affine.
Yeah, in the line of the clubbed gamma.
Yeah.
If I club of them will.
So you can do the predicate change, but you later realize that changing the predicate is harder than just changing the predicate. Okay, so like convolution is the linear.
So, but the gamma there has to be computed or
no, it's given in your L.
that is what is determined by that layer. It's quite mapping.
I mean, you know,
What, okay, my question is, gamma is the scale factor. Gamma
Yeah.
is it determined
yeah,
by
for
the
the
layer?
L.
For
For
the
the L, alpha, gamma and beta are. Yeah. He was just saying since gamma is fixed, you can just change the predicate variable and just change the predicate to a greater bound. Okay, so convolution is a linear operation. So you do the same thing. You change the anchor image, you perform the convolution on the anchor image, and you perform the convolution on the generator image without the bias, because definition B dash does not have the bias, no beta. The predicate remains the same. We do the same just so you can works. That's C, that's lambda. You calculate only for theta. Okay.
So there were two things there. Go back to your previous line. So there is convol.
Convol
Convol
is the
zero
convolution.
bias. Okay, you're going to show both of them in that example.
Yeah, so convolution is when you give a convolution layer, you give a bias and the weights, right? And convolution zero bias is just convolution without the bias. You just multiply the elements, don't add a bias. So like in this case, you do 0 into 1, 4 into 1, 2 into minus 1, 3 into 0. You get a value, and then you subtract minus 1, which is the bias, and then get this value. But you don't do that for the generator image. You directly get the value. So is there any doubt? Or should I explain how this works?
Gamma was also matrix, right?
Gamma was also
A matrix of the same size.
Yeah, like if it's fixed, but it's scalar. Like there's no variables in there.
Okay.
Yeah. Yes. So is there anything else?
I guess, yeah, it is fixed, but it can be
Like since this is a train set, you already have your convolution kernel. Okay, so next is average pooling. Now average pooling is also linear. You're just multiplying it by 1 and then dividing, right? It's also a linear operation. So the same thing, you do the average for the anchor image, you do the average for the generator images, you get the reachability set. This is the example. In average pooling, there's no bias, so both looks the same. Okay. Okay, next is a fully connected layer. So fully connected layer, adding weights, it's clear, Wx plus B, that's a linear operation, you can get it. But in fully connected layer, initially you have an image, right? And in DNNs, you need a single. You just flatten it, basically just pile all the rows together on top of each other to make. And this is also linear because it isn't really. Right. Yes. So the same thing, you do the convolution on the anchor image, you do the connected layer on the anchor image, on the generator images. Next is batch normalization. So if you guys do not know what batch normalization is already, is you take all the pixels, you make sure that that mean and variance are mu and sigma square. And so this is how you usually represent the pixel after and before. So after you normalize it, the CNN will learn and offset B and scale factor beta and scale factor gamma that the CNN will learn. And for now, you already have it. So all these values for you right now are constants. So if you represent it in this form, which is, this is basically normalizing it, and then this is basically adding the scale factor and offset. So you can represent like this, which is clearly linear in xi, since these all are linear. These all are constants. So just like we did in the previous case, you do the performance for the anchor image, and you do the for the generator images without the bias. Right. So far it's clear, no doubts. So far we used all the layers which have like, we can do an affine mapping for. Now we tackle max pooling.
So far, if I understand you correctly, everything is, so
Affine
far
map.
these transformations are affine and so they are precise.
Yeah,
correct?
so all the image stars we have reached in this is exact. It's not an over approximation, which is very important into why image star has a better result. Now comes max pooling. But max pooling, what you do is you find an area and you find the local max of that area. Now this can vary. Depending on alpha, this box can vary. So you can't exactly give an affine mapping. So in this paper, you give two methods, one that will give the exact reachability, and one that will give an over approximate reachability. The exact one is exact. It has its benefits, but it has too many image stars and there are negatives. So the method has come up with an over approximate method as well. So to visualize, so this is the question. This is the input you're given, and you have to do max pooling in this. So in this question, you have only 4 regions. And generally, you take all regions, but there's something called a stride. How many regions you take? Okay, so here you have 4 regions which you have to calculate the local max for. For 2 and 3, since the generator images have 0, it's kind of obvious that the local max here will be the local max for the general case. But in region 1, 4 plus alpha is there and 3 plus 3 is there. So it could be 4 plus alpha or 3 plus 3. Now, depending on alpha, the local max can change, right? So if alpha is like less than -1, then the local max will be 3. And if alpha is greater than -1, then the local max will be 4. 4 plus alpha, right? Now you can't obviously linearize this because it varies with how the alpha is. Sorry, yeah, right, alpha. Okay, so in 2, 3, 4, we know that it's obviously, we know the local max point, so we give it. But for 1, what we do is we split the alpha into 2 regions. So we split the alpha into -1 to 2, which is the region where 4 plus alpha will be max, and into the region between -2 and -1, where 3 will be the max. And for each of these separation, we show a new image star. So for this line, we give 4, 3, like in this region, 4 plus alpha is the maximum. So you give 4 as the value that came, and the generator will have 1. But we change the predicate. Like the predicate variable has a new bound, which is this, which is the interval where it works out. And you do the same for 3 plus 0, that bound you add. So like I said, in this, we are splitting an image star into 2 image stars. And okay, so for this, I gave you only 1 region. Now, all these regions could have a local maximum point problem. So, okay, so this is exactly what I've explained so far.
So how the number of local maximum possible, how is it is determined by the alpha?
So what we do is when we have regions, we kind of find the upper bounds. We have to find out if that region has an obvious local max or not, which is done by a few LP optimizations. You just have to find the upper bound and lower bound, check if there's an obvious one, right? And then you have this set of regions which do not have an obvious one. So in case 1 and 2 had a problem, you would split it according to 1, and then take those 2 image stars and again split it for region 2, just like later will become 4.
But how you split was not clear to me.
Oh.
Okay. So you, I mean, in this case, you split it so that each had a unique local maxima. But I don't know how do you know how to split the alpha values into finite number of things?
You have 2 values and alpha is bounded. So you can have linear optimizations which can find the interval where which is greater, which is greater.
I see. So you have to.
We have to have a lot of like a few LP optimizations.
LP calls, huh?
Yeah, which find the max. Right. Like I said.
Also, just to be clear on that point, the constraint that the value in particular pixel is greater than the value in another pixel, that is actually a constraint that is linear in alpha, right? So we're only splitting along some linear constraints. And then we can add them to the predicates, right? So is that a good description of what's going on?
My question was, how many cases of constraints?
Sorry, I can't hear.
So in this case, you had like 2 candidates, and both of these are kind of linear alpha. Okay. You can,
so that can grow as any number of different
local max, which I will talk about. So like in the example I gave you, there was just 1 region. But this could have happened for each point in the region as well as every single region. Now, if you split for every single such situation, you'll have too many image stars. So I calculated the paper, the complexity for this. If you're given that the max pooling layer is P1 and P1 comma P2, which is the size of the area you're calculating, then for each, so P1 into P2 will be number of elements in a region, and it's W into N be the number of regions you will have. Whole thing. Because if you're taking every single region, that's almost equal to the number of pixels. Right. Now this is a very now it gives an exact analysis, but in practicality possible for a large input set.
This number that you have is as many LP calls as you might need.
No, this is the number of splitting you will do. This will be the number of image stars you will have at the end of the one. Too big, and this is just for 1 layer. After this, each image star goes to a different layer. If you add it up, this method has an other over approximate reachability, which is okay. Let's take this example. So, like I said, the main characters are 3. So we know that we can we can find 2 intervals where alpha works. Now, what we do in this method is produce a new predicate called beta. This predicate beta is like the interval where the local max could be. Beta represents what the local max range for that region would be. So you add like 3 constraints, which is basically beta is greater than alpha, beta is greater than 3, which is and for this method, again, use LP optimizations to find the upper bound. We would have already done that to check if the region has an obvious local max point. So you will kind of have the upper bound of the local max in that region, which is what you give here. Alpha is bounded by 2. So the local max here is bounded. There's a lower bound and an upper bound. So now you can add it to the predicate. You add it to the predicate, and you get this is just one image star. You're just changing the predicate and your anchor image is generated. But theta, there's just one. And if you notice, since beta is the maximum point, you have a generator with just that pixel as 1 and the rest 0. And for the anchor image, you make it 0 for the generator. So the sum must be the local. So it is basically you have a predicate variable, which represents max condition 1. 3 constraints that you add to the fit. As I said,
Yeah, so I have identified like 4 reasons.
Yeah.
And so correctly, it's a 2x2 window.
yes. So I did explain it earlier because I didn't want to. But when you have a convolution, they also give you a thing called stride. Stride is how much the area
how
moves.
much you.
Yeah.
Yeah.
For
Instead
this
of one,
example, it's 2, so it moved by 2.
You get finer thing by you had alpha, then you introduce beta. You can have beta 1, beta 2, beta 3, and then you can keep going.
Yeah, so the idea is to just keep adding predicate variables every time there's a. So obviously you're changing the generator. Here you had one generator, now there's 2, right? So you're kind of adding a new generator as well. So each splitting is another predicate and another. But it's still less complex compared to the exact because you have too many image stars and later there's going to be a problem. So we calculate the worst case complexity of how many new predicates you will introduce. Now basically you add one predicate per region. So there's H into W, okay, that is times. Is it clear so far? This covers max pool and it's very important that this is clear.
So I have questions here.
Yeah.
So previously when the discussion came, you mentioned about changing variables instead of predicate.
Yes.
When you do a linear map, right?
Uh-huh.
I think considering the max pool is dependent on the predicate itself, not the values. I think for max pooling, it may be useful to change the predicate in the other cases.
So in this case, changing the predicate is more useful because in the other case, you're having new generator, like new image stars. But in the other case, you don't need that, right? Like you just can.
So that's exactly my point. Like maybe in some way, because in the other layers, if you take the predicate, the scaling factor to the predicate, you might end up with fewer constraints here because of the scaling.
The number, since it's linear, the number of constraints would remain the same, right? Even if you change the predicate, because you're multiplying it by gamma, right?
But in effect, you are changing the predicate here because it's becoming alpha beta. So the predicate has been changed. That's the way I understood. So the predicate has changed.
He was
But
suggesting.
maybe he's using it differently.
I believe his question is maybe even in that you could just change the predicate, no?
By changing the predicate, you
In
mean
the
predicate
affine
is a function of alpha, or in this case, if you add beta, it's a function of alpha and beta.
So in all the previous cases which are affine mappings, you are considering variables are changed, but the predicate is remain as it is, right? So if you are changing predicate instead of values there, which you could do mathematically as I see, maybe here when you reach, the predicate becomes shrunk or modified, in which case you don't have to introduce new things. It's just possible.
Yeah, this is like, since it's like the example I gave you is kind of linear. This has only there's one alpha, there's only one V. It might seem that changing the predicate is easier because there's very few constraints in the predicate. But if there were a lot more constraints in the predicates, changing your predicate variable would be complex. Like in this case, you're not exactly changing your alpha. the alpha's range is still between -2 and 2. It's beta that's a new variable that you're actually introducing.
Yeah, but I'm trying to understand. I don't know what it means to change the predicate, because the predicate here has a very fixed shape.
Yeah.
Okay, because it very much depends on alpha and the D that you have. So the predicate is always expressed as this whole thing being multiplied by that alpha and checking if it is less than or equal to each of them. There'll be as many constraints, linear constraints in the predicate as there are number of alphas, right? So other than that, what do you mean? I mean, I'm trying to see, what do you mean by changing the predicate? Because they have fixed the shape of the predicate pretty much as being expressed in terms of alpha and D, from what I can see. I mean, I don't know what it means to change the predicate beyond that, okay? Other than changing the number of alphas you have, and then,
So the thing you're
just like you're
suggesting
doing here.
is like, if you change your predicate variable in like affine mapping, this intervals would be different. So
Yeah, the D
ideally, in
will be
an ideal situation, since you're changing your predicates in your affine mapping, there might be a particular case where if you had like, okay, I have to go back too many slides. But if you had changed the predicate variable instead of the generators in your affine mapping, then this bound would be different. And then like the local max would be obvious. Like you wouldn't have to do the splitting.
So is that being a possibility? Is that the question?
Yeah, that's the
But
question.
I have a more fundamental question. I don't even now understand.
Oh,
the only way you're checking the predicate is given a D and an alpha, I check those constraints.
So here instead, like we never do it, just a suggestion. But you're doing gamma VI, right? Instead of like you replace VI here and lambda I here. So you kind of
Yeah.
But there's also the case where gamma is not a real number. Like alpha I won't actually, alpha I here has to be a scalar. But if you multiply it by gamma, it may not be. Gamma can be.
No, so I think there is, I think, a slightly different language in which this can be viewed, where this I feel like this question becomes clear. If you really look at the image star, it is in some sense talking about a space of allowed values and then a linear expression involving some CNV, right? So in some sense, it is a piece of a linear space, right? Now you're mentioning that you'll change the, like you say, that you can change the predicates potentially in when you're doing propagation across these linear, like affine transformation layers. And maybe that will give you, get you into a situation where in some other layer you would have situation where you don't have to do a split or do an over approximation. I don't think that is the case, because if you are changing the predicates in any way that is still mathematically equivalent to whatever you had before, you would still just be talking about the same piece of a linear space, just in a different basis or with different variables. So this possibility, so for example, if we talk about this max pool layer in region 1, there is a possibility that you can be, the max can be in 1,2 or it can be in 2,2, right? So either the pixel that has got a 4 currently can be max, or a 3 currently can be a max. I think the possibility that both of those are possible will still be there, even if you're changing the predicates, because it's still underlying the space you're talking about, the possibilities of images, the space of images you're talking about is still the same. You're just doing a slightly different representation of it. So I think from that point of view, doing a change there, I don't know if I don't think that it will give us any benefit here. So because, underlying the representation that we have of an image star is linear, that's why whenever we have an affine transformation changing, we don't need to change the P, but even if you were to change the P so that everything is still mathematically equivalent, we won't really gain or lose anything by that. So I don't know if this comment sort of addresses your question in any way, but yeah, this is one thing that felt.
Yeah, so what you're saying is that even if you choose, give the freedom to change the underlying cause for these things will still remain the same.
Yeah,
Or
yeah,
some
yeah.
other
They'll just
form.
add up.
Yeah. Because I mean, it's not that we're changing the underlying space anyway. We're just changing the representation, and I mean that I don't think inherently will give us any benefit further down the line. The issue that we're having to do the split or do the over approximation, the issue behind that is you know, having two possible active phases or two possible maximum values, which is still going to be the same situation, right? Because that depends on the underlying space of possibilities. Yeah, that is what I'm referring to.
The over approximation here is coming because you have not split.
So
You're reducing the number of splits.
yes, and it's an over approximation because beta technically is the range in which the local max can be, but in the exact, like in the exact local max. Yes. It's an over approximation. Then there's layer, which is similar, which has a similar ideas as this. So we need, first of all, for each pixel, you need to check if you have to find out the lower bound and the upper bound, and if like both of them are positive, then it's fine. Fine, because ReLU is obvious then, right? So we just have to consider the case where the lower bound is negative and the upper bound is positive, and this can be done like you can calculate the lower bound and upper bound. Right. So there's obviously two methods. Exact analysis. So here's the example. So if you have this, it's the only thing that causes troublesome is -1 plus alpha, the first one. So we can just like we did in max pool, find the interval where alpha is, where this would give a negative, and find the interval that would be positive. So in this case, -1 plus alpha, so alpha between 1 and so like so how this works is you do it for each pixel. You kind of check for one pixel if the lower bound, and you do that for the next pixel. You kind of have to do this step ReLU operation for each. So if we were to split at every time, like every pixel you go to, you'll have kind of 2 bar n. 2 bar n. Like I said before, is a big number, and this would be very complex when you have to check it. There are too many. So we also have an over approximate here. So three constraints you add are beta is greater than 0, ReLU, and beta is greater than x, like the value of that pixel, which is 1 for here. And then ReLU, we also have this bound, which you can visualize here. If you're given a lower bound and an upper bound, this value, which is this line, always be above the ReLU. So we can always add that constraint. Now, beta represents, like I said, all the range of values you can get by passing. So, right. So now beta has an upper bound.
Similar to what deep poly does.
So, yeah, so you have an upper bound and a lower bound for a predicate. Right. And if you were to add predicate variables, you just add the number of pixels. 3 is the number of constraints. Right. So now you know how to find the reachability set after for all types of layers. Now, like I said, I showed you R1, how RL1, RL2, Rn. So we do that here. Like I showed you earlier, the affine mapping layers are exact reachability, but the max pooling and RLU, you have option of exact or over approximate. So the algorithm gives you an option. Start the algorithm, you decide whether you want to go exact. Not clear here, but like N is your CNN, all the layers. M is whether you want to be exact or approx, and I is your input set. So you pass it through all of these. You finally get an Rn, but this would be an image star of like a single array of all the values which you're supposed to do in the CNN, like a softmax or an R. So like in earlier, we were able to find the range, like the upper bound and the lower bound of the pixels, right? We can do the same in this case. The final Rn you get, you can find the range for each pixel and find if there's a pixel for which the range is above all the other ranges. If such a range exists, then the image is robust. If there's two ranges where they clash, no, because there's a possibility where another pixel could be the R.
Here you're splitting image set into smaller image set. It's not for each pixel.
No. Okay. No, I was talking after this. Like after this, you get an Rn. For this Rn, it will just be like a bunch of arrays which the actual CNN you would do activation function, right? To classify it as a dog, a cat, you have to find the softmax or the app. Now that's not a linear. You have to do it. You find the upper to be like. I was hoping to show you later, but this is how it will look somewhat. This is the range. Like this is for digits, and the red part shows the range of all the pixels or the outputs. Outputs. Sorry, I'm not.
The output.
The output. Each element in the output.
All of the cats.
Yeah. So if all of them are cats, it's robust. If it's not, so the thing is, if we do an exact, so if we are doing an exact, like if you choose a scheme to be exact, and you find an output for which it's not cat, then you know definitely that there is an adverse, like there's a thing in the input set which is labeled wrong when you pass it through the CNN. So you can say it's not robust. But if you use over approximation, you obviously get an over approximation of the last layer. So you can't technically say that the image is not robust. There's still a chance that it is robust, but you got a very bad over approximation.
Here in this algorithm is using some parallelism, that's okay. And so each thread in that parallel thread computes one image in the output image. Outputs that you can get, right? So for each of them, there is a check that is probably done. Because see, here R for I to I is equal to 1
That is
to
that
n.
is the different layer.
What is to n? What
1
is
to n. So there are n layers.
Small n. What?
Li here.
I
think that's the same one.
capital N is your input. Oh, no. That's the number of layers.
Yeah, so each Li is a layer. And I here is the index for each layer.
Yeah, for each layer,
And then
you pass through each of them.
Yeah, reach scheme is the process I explained till now.
Yeah. So okay. So you're only parallelizing each layer. No, but then how can you parallelize each layer? So you'll have to wait for each layer. What is being parallelized here? I don't understand. What is being parallelized here?
So, like, if you're doing, like Like if you
no,
if
but
you
see,
have-
but you don't have that because here the entire set of images is represented as this image star symbolically as one of a formula. So you cannot split that.
I think the thing you can parallel is in case like if it's an exact, you can't parallel. But if it's an approx, you kind of split it into two image stars, right? You split your initial image star into two.
If it is exact, you can split into two.
No, yes, sorry, right.
Yeah.
Yeah.
If it's exact, you
If
can
you split it two, and then you can parallelize after that.
Yeah, in that
But if
case,
approx,
your RN will be multiple. I mean, there'll be multiple outputs.
yeah,
huh?
there will be multiple.
So there is
outputs.
some union that is missing here when you have a parallel thing.
Yes,
Okay.
it's-
Yeah, now I understand. So I think when you split, you have a separate thing, and then
you
that
can,
means
like,
completely
parallelize.
separate. For that condition you get, for that split, you get a separate output for which you can check.
Also, you have to do operations per image in the permutation set, in the perturbation set, right? It's like the set is like V, and you have to multiply gamma for each V, and then when
Yeah.
you do split, you have to do that for
for each.
alpha I.
Yeah, but like for all the examples I gave you, even if the V were more, there would be only one image star for over approx. If that's clear, right?
Yeah, so within one image star, you'd have a lot of
Yeah,
perturbation matrices. Which you
Yeah.
have to- So you could parallelize that problem.
Right.
Yeah, so that is, I think, a
Yeah,
good point.
yeah.
I mean,
Yeah,
this
since
is
you have
something.
different generated images,
Yeah, go on.
because you have a lot of linear optimization. So can also be parallelized, like finding the local max. If it's like the upper bound and the lower bound, that can be parallelized. They don't specify what all they parallelize. They actually don't even talk about it. I just
Yes, no. So the only thing that the paper actually mentions about parallelization is the splits. But yeah, I think there is a lot of opportunity for parallelizing this algorithm. I think, I mean, the only place, like even if you look at the operations being done, there is a lot of large matrix multiplication sort of operations being done. That those can be even parallelized on the GPU, for example, right? But the only place where I think the parallelization, when you're doing the over approximate analysis, might become a little difficult is that you have this central set of predicates. So every sort of parallel threads needs to ship some, like it's going to handle some part of the computations. It's going to ship some value to be added to the central set of predicates. So it can get a little bit complicated along that lines. But yeah, there is a.
Because that requires some synchronization.
Yeah,
Whereas
yeah.
higher level, you don't need any synchronization. Once you split, it's a completely different problem.
Yeah. But yeah, I think that there is potentially some scope there. It's maybe not like very immediate, at least to me, but yeah, it's definitely possible to parallelize across generators or even within generators for these large matrix operations also. That was a very interesting point.
So next, so we have explained the algorithm, how it works. Check, like compare it with the poly and the thread, see how it performs. The first experiment is you take 3 CNN and you have 3 different types of CNNs. One is medium, one is large. Basically, the input is and with accuracy 98%, 99.5%. The MNIST data set is just a data set full of digits of 28 into 28 pixels. So we are going to demonstrate an adversarial attack with the input. So what we do is we take an and the adversarial attack we are going to use here is a brightening attack. That is the pixels value of it. Right? So in this case study, if a pixel of an image is greater than a threshold, then you give it like you reduce or darken it. So you reduce it to within this range. If you represent this in the form of an image star, delta will be the predicate variable, and So how according to me the thing will look is because this brightening and darkening is independent. Brightening of one pixel is independent of brightening of the other pixel. How the generator, so the anchor image will look the same. Anchor image will look the same, but yes, yes. Okay, okay, and like the bound is 220. Is 220. So this is the only pixel which is greater. So your input image will kind of look like this is the anchor image. And the generator will be 0, 3, 2, and your predicate variable will be delta, which is no, yeah, which is alpha, which is bounded by delta. This will be a predicate variable, and delta is fixed. Okay.
Yeah, but is delta the function of D?
No, like it's D is fixed, delta is fixed. They are independent of each other.
But the relationship.
No, I think this delta will be less than 1. You're reducing it, right? So I don't think it will cause a problem. D is just a threshold because we don't want to darken everything. Like if it's too dark already, there's no point of. We just take elements which are bright enough to actually cause a proper darkening. So this is a bright pixel. These are like dark enough. So this is the range, right? This is what? No, 0 and delta. Yeah. So the input. So this is our image star of the input, which is this. V is just this generator. Predicate is sorry, the other one. This is basically minus lambda. Like oh, sorry. Oh. Yeah, I'll go between 0 and 244 into that. Yeah, that pixel. But if there is more than, like if this was also 230, we'll just add another generator for 0, 230.
That's what he determines.
And this will have another alpha I, but this same bound. So you can picture the input.
That image, and then you
Yeah. Will be between 0 and 244 into delta. This is a smaller value than 244. You are, because that's still the anchor image. Oh, fuck. That must be 0. Your anchor image, you should make it 0. About the threshold. kind of like the cat with the pixels you don't care about still remains the same. Okay,
But
yeah,
not in this
technically,
case, right?
yes, it's not the exact same cat. It's
Right.
just,
So in this case, you're not adding any pixels which are sufficient, which are bright enough. Right? In this case, you're darkening every image to below delta. No, but delta is 1, so that's fine. Okay.
okay.
Yeah, I kind of get the, it's not completely clear, but no, but as other parameters, the size of the window is not a parameter in these experiments.
Size of the window?
Kernel, the size of the.
So that's already given, like it's fixed for the CNN, right? You have given 3 CNNs where the kernel is fixed. It's trained. You have the train.
No. I thought these 28 by 28 pixels is
Yeah.
the complete image size, the total number of pixels.
So each image in the data
Yeah,
set
but the
has
convolution layer usually uses a kernel of a certain size,
yeah,
which then.
which depends on the CNN we used in the experiment. We don't
Yeah,
know
but
which
I see that as not a parameter in.
when testing.
Oh, in the CNN.
Yeah.
For each of those CNNs, that's where the small, medium, large CNN
So
is
basically,
measured in terms of the
number
number of
of-
pixels.
No,
Number of.
like it could be the
Number
size of the kernel or the number of layers.
Right, that's what is not clear here.
Yeah, they haven't
Yeah.
specified. It just gives a better results compared to the
So
smaller
they
ones.
haven't even talked about the size, the total size of the CNVs, is it? Yeah.
So the results. So what the experiment does it? They do this adversarial attack on 100 images. You pass it to each image, pass the adversarial attack. It's robust or not. So we compare it with the polytope method, which is deep poly and deep set. In this table, there's no deep set because deep set did so badly that they didn't. Right. So this is the small CNN. You see that. So this number is how many images came out to be robust among the 100. You can see that there. Okay, ours does give a bigger value compared to the polytope, but it's somewhat similar. And you can also see that the verification time of polytope is better than ours. It is now we compare it for the medium.
Your delta
changes.
increases,
Yeah.
even then your polytope is much better.
Polytope's verification
No,
time is
wait a
much
minute.
better.
What is the number there?
This is the number of images among the 100 which came out to be robust. Like the algorithm said that the image is robust, which is that everything in the final image star gives the same result.
No. I thought that the number there in the first table, that one was how many it was able to
could survive the adversarial attack.
certified that it was robust. No?
Yes.
But is a lower number for polytope better for polytope or
no, lower number is bad because
bad? Yeah. So which means
like if image star had show 71, then there's 71 images that could have survived the attack, but polytope could only find
was able
65
to only check 65. So which means as delta increases, image star is doing better. Huh?
I mean, the numbers are kind of
pretty close, yes, but strictly it's doing better than say
polytope,
right there. Huh?
Yeah. So for small, it's kind of similar, but in medium, you can clearly see it. For example, for D240, polytope can get only 38 and ours can get 88. So there is something we noticed that the verification time for polytope is way bigger than ours. So the paper does not have an explanation of why exactly this is happening, and we should probably.
Just to be clear on this, when they're talking about polytope, they're actually talking about deep poly, right?
Yes.
Yeah,
poly.
so it's not just it's not a complete polytope-based method and deep poly. And comparing with deep poly, it should be similar time itself. So this is somewhat surprising and hard to explain, and the paper doesn't talk about it.
Yeah, the question here was whether these numbers are for exact method.
Almost over. Okay, so for bigger ones, you notice that the polytop has a memory error issue. Oh, okay, so I showed you this before.
I didn't know this. This is some class.
The range we got, the range we got. This is absolutely correct. And this is clear. Good. So this is for one image. This is a digit. Can you tell me which digit this output? Okay. Right. So this is experiment 2, which uses two real words. And it has 13 convolution layers, 3 fully connected layers, and it has more similar but lesser convolution. Right. So what we do is box adversarial attack. So basically, for so you take that adversarial, the difference to kind of fix L is the percentage of adversarial attack you want to give to the image. So basically, you just keep changing XNL to check if the image is reversed. And here delta is the predicate. You kind of change delta between basically REM plus L is like active image, and this IM will be your generated image, and delta will be your predicate variable. And you have bounded the predicate variable. Okay, so this comparison is polytope and image star gives some of the same results in the time. But this is one cell paper image. So compare between our exact feasibility and so what this does is how much percentage of attack and delta max. So this is one image. Okay. So here you'll notice that for exact says no, it will not. But approximate can only. So this is basically whatever I said. So you have to do a lot of upper bound and lower bound. Just add up to a lot. The paper says that the next feature. Now, this paper came out a while back. 20 is an absolute. But now there's alpha beta crown, which does not use LP optimization and has a way better result. So from this, you get to know that image star gives a way better result.
So I think we never got to the question that
Yeah,
I think, but that's
so-
okay.
so
No,
we
no, no,
clear-
there's no time.
No,
for,
no, we-
zonotopsis.
So we
Okay.
clearly saw that.
No, the advantage is there as to why,
Oh, why?
what exactly is
Okay.
happening and how is modeling this thing in zonotope and polytope, the propagation is different is what I would
So
get.
the thing is,
Maybe that will be the, no, I think.
no,
we
it's the
don't
one
have
line. So
time to just-
depoly does not have exact reachability as much as image star does, right? So it does not give as good as robustness.
Yeah, it could be one thing. Yeah. I mean, I also wanted to know how exactly you would model the thing. Okay. So let's thank Jessica.
Thank
and
you.
then,
Thanks a lot.
yeah, we're done. They got that.
Uh,